bond energies and bond lengths. So a little bit back to that thermochemistry kind of stuff. We learned that we can estimate enthalpy changes using heats of formation. We can also estimate it using bond energies. The bond energy is the energy required to break 1 mole of the bond in the gas phase. Bond energies are always positive. It always requires energy to break the bonds. That kind of makes sense, because if it released energy when the bonds broke, they would spontaneously break themselves, right? And they wouldn't exist to start with. A stronger bond takes more energy to break. So here we have an example of an equation showing the bond energy. We've got hydrogen chloride molecule, and it's coming apart into a hydrogen atom and a chlorine atom, all in the gas state. Delta H for that is 431 kilojoules. So that's 431 kilojoules for 1 mole of HCl. So that's breaking 1 mole of HCl hydrogen chloride bonds. Compounds that have stronger bonds tend to be more stable. That makes sense. Like if your Lego blocks are super glued together, it's going to be harder to react them and take them apart than if they weren't super glued. So they'll be less reactive. Well, the bond energies are going to be different depending on what molecule it's in, so that's not so useful. So we use an average bond energy. And so we average the bond energies for a bond between 2 specific elements in a large number of compounds. If we look at a carbon-hydrogen bond, if the carbon-hydrogen bond in methane requires 438 kilojoules to break a mole of those bonds. If we have the 3 fluorines here instead of the 3 hydrogens, it requires more energy, 446. Bromines would be less, 402. Chlorines would be less, 401. Now, why some are less and some are higher is a subject for a different part of chemistry. But we look at the average, and so the average carbon-hydrogen bond energy is 414 kilojoules. And so they're going to average the carbon-hydrogen bond energies from a bunch of different compounds. Double and triple bonds have higher bond energies. Kind of makes sense, because you have 2 bonds to break, it's going to require more energy. Here's a table of bond energies. You don't memorize these things. You just go look them up. So here, these are in kilojoules per mole of bonds. And the one thing I'd like to point out here is the carbon-oxygen double bond. There's an asterisk here. And we come down here, that's what the asterisk means. Go look for the other one and see what it says. 799 in CO2. So if you're dealing with CO2, then you have to use this number. Anything else with a carbon-oxygen double bond, you use that number. So how can we use bond energies to estimate heat of reaction, enthalpy change? Well, breaking a bond is endothermic. You have to put energy in. And forming the bond is exothermic. So we're going to add the energies for all the bonds that are broken and formed and see what the difference is. It's a little bit like accounting, where, it's like, well, how much did you invest and how much did you get back and what's the net result? Was it positive? Was it negative? Was it really good or just a smidge good? So the bond's broken, that's the investment. I have to put energy in to break these bonds. And then the payback is the bonds being formed. It's the bond energy with a minus sign in front of it. So the reaction will be exothermic. It will release energy if the bonds that are formed are stronger than the bonds that were broken. We can draw a Born-Haber cycle type picture for this. Here we're looking at methane reacting with chlorine. So We have CH4 plus Cl2 making CH3Cl plus HCl. That's the equation, the reaction. So in order for these two molecules to react, we have to break one of these carbon-hydrogen bonds. And so that's going to require us to put some energy in. We're also going to have to break this chlorine-chlorine bond. It's like with Legos. If you have two little Lego things and you're going to make a new thing, you have to take some apart, right? So I have to take these two apart and I have to pull off one of these hydrogens. And so I can figure out the amount of energy required to break those bonds. Then I'm going to form a bond between hydrogen and chlorine, and I'm going to form a bond between chlorine and the carbon here, and that's going to release energy. And the heat of reaction is the net difference. Does that make sense? Once you get it, it's actually really simple. Oh, we're just taking the Legos apart and we're putting them back together. How much energy to take those apart? How much energy gets released when we put them back together? Add them up. We often talk about energy being stored in chemical bonds, and yet breaking a bond requires you to put energy into it. It's the forming of bonds that releases energy. An energy-rich compound, we would say it has a lot of chemical potential energy. It undergoes a reaction in which weak bonds are broken and strong bonds are formed. So it's kind of the opposite of what you sort of think. Energy is released when bonds are formed. Okay, let's look at this conceptual problem. The reaction between hydrogen and oxygen to form water is highly exothermic. Which statement is true of the energies of the bonds that break and form during the reaction? The energy needed to break the required bonds is greater than the energy released when the new bonds form. So if it takes more energy to break the bonds than the energy that gets released, is that going to be exothermic or endothermic? That's going to be endothermic. Overall, it's going to require energy. So that can't be the case because it says it's highly exothermic. The energy needed to break the bonds is less than the energy released. That sounds right. And then let's check the last one. The energy needed to break the bonds is about the same as the energy released. No. That could be exothermic, but it would just be a little bit if they're about the same. And this says highly exothermic. Any questions? Okay, we're going to do a problem. So a potential future fuel is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. So what we want is how much energy in kilojoules is released when 1 mole of methanol burns. So the first thing we need is a balanced chemical equation. So we have CH3OH. And it's combusting. What's it reacting with? Oxygen. Because all combustion reactions involve oxygen. And what are the products? Carbon dioxide and water. Because that's what they always are when you're burning carbon, hydrogen, and oxygen. So then we go to balance it. I like to start with the carbons. I have 1 carbon and 1 carbon. So far, so good. Hydrogens, I have 3 plus 1. That's 4. And over here, I have 2. So if I put a 2 in front of the water, I get 4 hydrogens. And then the oxygens, I have 2 oxygens here and 2 oxygens there, a total of 4. And over here, I have 2 oxygens and 1 oxygen is 3. 3 is not the same as 4. So I have two options. I could use a fractional coefficient, or I can double everything. The thing with doubling everything is I'm trying to calculate the amount of energy for 1 mole of this. So what I did yesterday in lab is, in my lecture, is I doubled everything, and then later we divided it in half. So I'm going to do the other thing here. So I've got 1 oxygen and 2 oxygens, and I want to have 4. If I multiply 3 halves by 2, 1 plus 2 times 3 halves, the 2's, that ends up being 3. You might say, well, I don't like that. Well, you can do it the other way. Okay, so now we have to figure out, well, what bonds are being broken, what bonds are being formed. There is a bond that's not being broken, but most of them are getting broken. And I think it's conceptually much simpler to just say, let's take them all apart. Let's break all the bonds and then make all the bonds. That's not actually what happens, but it's easier because we don't have to identify, well, which ones are staying and which ones are not. But we do need to look at the Lewis structure so we know what kinds of bonds we've got here. So for methanol, oops. Oh, that's wrong. That's not. Methanol is going to look like that. And oxygen has a double bond. And then CO2. The point of this is not drawing the Lewis structures, that's why I'm just kind of doing them fast for you. Because I need to know, are they single bonds, are they double bonds, how many, what are they between? So I'm going to look at my reactants here, and I have 1 mole of methane. So in this 1 mole of methane, I have 3 carbon-hydrogen bonds. Do you see that? There's 1 carbon-hydrogen, 2 carbon-hydrogen, 3 carbon-hydrogen. So I have carbon-hydrogen bonds, and I've got 3 of them. 3 moles of those bonds in 1 mole of methanol. Everybody okay with that? I have 1 bond here, 1 bond there, and 1 bond here. That's 3 that are between carbon and hydrogen. Carbon-hydrogen is a single bond. Then I also have a carbon-oxygen single bond. Just 1 of those. And I have an oxygen-hydrogen single bond. 1 of those. Okay with that? In the oxygen, here's O2, I'm looking at an oxygen-oxygen double bond, right? So 1 mole would have 1 mole of bonds, but I have 3 halves of a mole, right? I'm going to write 1.5, that works too. On the other side, with CO2, each CO2 molecule has 2 carbon-oxygen double bonds. A mole would have 2 moles of carbon-oxygen double bonds, right? So here I've got carbon-oxygen double bond. I've got 2 moles. I've got 1 mole of this. I'm going to have 2 moles of the bonds, because in each molecule there are 2 bonds. Each water has 2 hydrogen-oxygen bonds. or oxygen, hydrogen. So 2 of these in every one of those, and then I've got 2. So 2 hydrogens per mole times 2. Everybody following? Now I need some numbers. I know the one for carbon dioxide, but I don't know the rest of them. So, going back to this table, I'm writing on the board. A carbon-hydrogen bond is 414. I had some of those. I had oxygen-hydrogen, 464. I had carbon-oxygen double bond in CO2, so 799. Let's see, I had a carbon-oxygen single bond. Carbon-oxygen single bond, 360. I think that's it. We'll find out. So now I can go back over here, and 3 moles of carbon-hydrogen bonds. Each mole of them takes 414 kilojoules. And I have 1 mole of carbon-oxygen single bonds, so that's 360 kilojoules. And I have 1 mole of oxygen-hydrogen bonds, 464 kilojoules. Oh, that's the one I forgot. Forgot the oxygen. Oxygen double bond is 498. kilojoules for 1 mole, but I have 3 halves. This is all things I'm breaking, so I'm putting energy in, so it's a positive number. So I can add this up. 3 times 414 plus 360 plus 464 plus 3 halves times 498 equals. I'm getting 2813. Anybody else get that? No? Let me try again. 3 times 414 plus 360 plus 464 498. I got 2813 again. So I'm going to go with that. Then the bonds that I'm making 2 moles of carbon-oxygen double bonds, so that's 2 times 799, 2 times negative 799 kilojoules. Negative because these are forming, not breaking. And then I have 2 times 2, 4 moles of hydrogen-oxygen bonds, 464, and left minus kilojoules. So 2 times negative 799 plus 4 times negative 464 equals minus 3454. That's the payback. That's what gets released. So Delta H for this reaction then is the sum of those. (2813) plus negative 3454. Negative 641 kilojoules.
So if you were to look this up, the actual change for the reaction, and then also do this like a Hess's law problem, you'd get roughly 641.
Yeah, you should get a similar result if you looked up the heats of formation and added those up. Yeah. Now, because we're using average bond energies, this is not a super precise number, but it's relatively easy. Any other questions? Yes. So why is the one side positive and the other side is negative? This is positive because positive means I'm putting energy into the reaction. So, if you're trying to identify the sign, you have to decide, well, what's the system? What's the surroundings? The system is the reaction, like the methanol molecule. And so to break my bonds, you have to put energy into me. That's money coming into my wallet. That's a deposit. Here, we're making the bonds. That's the opposite. Making bonds releases energy. So same number, but with a negative sign. Any other questions? Bond lengths pretty much correspond inversely with bond strength. We see that triple bonds are shorter than double bonds, and single bonds are longer. And the strength goes opposite. A triple bond is strongest, a double bond is in the middle, and a single bond is the weakest. That makes sense. And the shortness, you think, well, the two carbons with the triple bond, they've got 6 electrons. That brings them closer. They're just like really getting tight in closer to each other. In general, long bonds are weaker, but of course there's exceptions. There's a table of bond lengths. I'm not sure if you actually need that table at all, but there it is.